Hi everyone, it's Nasekun with HSIM, a hierarchical eigensolver for Laplace Beltrami Eigenproblems. This is a joint work with my supervisor, Klaus Hildebrand from TU Delft, the Netherlands. Large-scale sparse eigenvalue problems arise in many applications of computer graphics. One important example is the computations of the low and medium frequency spectrum and the corresponding eigenfunctions of the Laplace-Beltrami operator of a surface. These are at the heart of approaches for shape analysis, such as the heat kernel signature and functional maps. They are also used to extract low-frequency features in geometric deep learning schemes. In mass processing, Laplace eigenfunctions are used for shape modeling and optimizations, and also for mesh segmentations and remeshing. These methods require us to solve large-scale sparse eigenproblem, in which, given the stiffness matrix S and the mass matrix M, we are to find the eigenfunctions phi and the eigenvalues lambda that satisfy the following equation. The state of the art is to solve those systems with Lanczos methods. The commonly used is the implicitly started Lanczos method implemented in RPEG, MATLAB for example using RPEG. Spectra offers a re-implementation using the eigen-sparse matrix library. And one alternative is the band-by-band shift and invert Lanczos method that is implemented in Bruno-Valli and Bruno-Levy's manifold harmonic solver. All of these are highly efficient eigensolvers. Another option is the subspace iteration method, which is known for its robustness. However, Lanczos methods are often preferred as they are faster. We introduced HSIM, the Hierarchical Subspace Iteration Method, which is a multi-grid eigensolver for sparse eigenproblems on surfaces, based on the subspace iteration method. Our evaluation shows that it can solve Laplace-Beltrami eigenproblems up to 2 to 10 times faster than state-of-the-art solvers. Before we dive into the new multi-grid solver, let us review how the subspace iteration method solves an eigenproblem. The basis of this method are power iterations. Power iterations can be used to compute the lowest eigenpair of a positive definite matrix S. The idea is to start with a random vector and to iteratively multiply the vector with the inverse of the matrix, and then normalize the resulting vector. The vector more and more becomes the first eigenvector with every iteration, and the iterations are stopped when it is close enough to the desired eigenvector. While the inverse power method computes only one eigenpair, the subspace iteration method computes the p lowest number of eigenpairs. The initialization starts with the p random vectors stored in one matrix phi. Then we iterate two steps. First, it is an inverse iteration of all p vectors, and this shifts the vector towards the low frequencies. The second step is to solve the eigenproblem restricted to the subspace spanned by the current vectors. And this auto-normalizes the vectors and results in approximations of the lowest p eigenpairs. The iterations are stopped when all p eigenpairs converge. This is only the basic versions of the subspace iteration method, and many extensions are possible. One important point for us is that if one wants to solve a generalized eigenproblem, one only has to insert the matrix M into the inverse iterations. And another point is that one can shift the matrix to make the iterations more effective. We refer to the paper for a discussion of this and more extensions of the basic scheme. The subspace iteration method is a reliable solver for generalized eigenproblems, but often not as fast as Lanczos schemes. We have developed a hierarchical subspace iteration method in which subspaces iterations are performed on different levels of multigrid, with the goal of significantly reducing the number of iterations required on the finest grid, and thus speeding up the computation. The starting point for describing our hierarchical subspace iteration method is the constructions of the hierarchy on which the method operates. Since the eigenproblems we consider are posed for functions on triangle meshes, we construct the hierarchies on meshes. And to do this, we first build vertex hierarchy. And then we construct prolongation and restriction operators that map function between levels of the hierarchy. We build the vertex hierarchy using vertex point sampling. It starts with selecting a vertex and iteratively adds the vertex furthest away from the current sample vertices to the sampling. So we first construct the coarse level by randomly select a vertex. And then the second sample is the one farthest away from the first sample. The third sample is a vertex farthest away from the two chosen samples. And we iteratively perform farthest point sampling until the desired number of points has been reached. The second level then starts with the vertices of the first level and uses farthest point sampling to add more vertices until the desired number of points for this level is obtained. This process continues until all levels of the vertex hierarchy are constructed. The number of vertices per level is determined by a heuristic that we describe in the paper. Once the vertex hierarchy is constructed, we need to define the prolongations and restrictions operators that map function across level. Restriction operator maps function from finer to coarser level, while the prolongation operator does the opposite. It maps function from coarser to finer. To construct the prolongation operator that maps from level tau to level tau minus 1, we define a geodesic disk around each point of level tau. On the picture in the middle, we see the sphere of influence of a vertex in red and the vertices of the next finer level in blue. For each blue vertex within the influence sphere, an influence weight is defined based on the geodesic distance. It determines how strongly the vertex of the finer level is influenced by the vertex of the coarser level. And when all weights are computed, they are normalized to produce a partition of unity. The weights are collected in the prolongation matrix U, in which a column corresponds to a single geodesic disk. The first column corresponds to the disk centered at sample 1, the second column corresponds to the disk centered at sample 2, and so on and so forth. This matrix U is sparse by constructions, since the disk is locally supported. We do this for all levels, including from level 1 to level 0, in which one of the disks is shown in blue. The restriction matrices are constructed by transposing the prolongation matrices. With these matrices, we can map functions up and down a level of the hierarchy, and we can construct restricted matrices for all levels. Now we can describe the hierarchical subspace iteration method. The first step is an initialization in which we compute the hierarchy and the restricted matrices for all levels. Then we compute the approximate eigenvectors on the coarsest level by solving a dense eigenproblem. The coarsest level of the hierarchy is constructed such that the dense eigenproblem can be efficiently solved. Usually the coarsest level has 1000 vertices, but it can be larger if a large number of eigenpairs is desired. Once the vectors in the coarsest level are computed, we iterate over the hierarchy from coarse to fine. On each level, we prolongate the vectors from previous level, and then we perform subspace iterations on the level until convergence. During this process, the approximate eigenvectors become sharper and sharper. On the left, we see an intermediate approximate eigenvector, and on the right, we see a converged eigenvector. This outlines the basic algorithm. More details are described in the paper. Let us now look at some of the results. We evaluated HSIM on the computations of the lowest Laplace Beltrami eigenpairs on triangle meshes. This slide shows a comparison of the performance of the subspace iteration method and the proposed HSIM for the computations of different number of eigenpairs, ranging from 250 to 2500 on a mesh with 270,000 vertices. Each number on the table indicates the number of iterations per level. For example, F21 means that we solve using GPU solver on the coarsest level. Then we have 2 iterations on level 1 and 1 iterations on level 0. We can see that the subspace iteration method in all cases require 8 iterations. For HSIM, we list the iteration count on different levels. To compute 250 eigenpairs, for example, HSIM uses 3 levels. For the coarsest level, no iteration counts are listed, as the solver is used. HSIM requires 2 iterations on the second level and only 1 iteration on the finest level. The same iteration counts also hold when more eigenpairs are computed. This means that HSIM successfully reduced the number of iterations required on the finest level. And this is also reflected in the timings. HSIM achieves a substantial speedup. As the timing for HSIM also includes the time for hierarchy constructions, and for iterations on the coarser level, the factor is not exactly 8. However, for the most difficult problems, like the computations of the 2500 eigenpairs, the factor is close to 8. Let us look at the breakdown of the time spent on the different levels of the hierarchy. We consider the computation of 200 eigenpairs on a mesh with 150,000 vertices. The constructions of the hierarchy with 3 levels takes 4 seconds. About 1 second is spent on the coarsest level, 10 seconds on the intermediate level, and the major part of the computation time, 42 seconds, is spent on the finest level. At the finest level, about 10% of the time is spent on the prolongation of vectors from the intermediate level to the finest level. The remaining 90% are spent on the subspace iterations on the finest level. And these can be further split into the timings for individual steps of the subspace iterations. Among those steps, the inverse iterations require the major part, almost 50% of the computational time. We also conducted experiments to explore how the runtime scales when the number of eigenvectors to be computed increases. The graph indicates a linear growth of runtime. The reason is that for the shown number of eigenvectors, the most expensive step is the computations of the inverse iterations. And the cost for this scales linearly with the number of eigenpairs to be computed. At some point, however, the solving of the eigenproblems in these subspaces will be more costly than the inverse iterations. The computations then do not scale linearly anymore with the number of eigenpairs. Our experiments indicate that this nonlinear behavior only starts when several thousand eigenpairs are computed. We experimented with the number of levels that we use in the hierarchy and found that low number of levels, namely 3, performs best in most cases. Only when less than 100 eigenvectors are desired, using 2 levels perform best. The table lists more details. We can see the iteration counts and timings for 2 to 5 levels, for 2 meshes, and different number of eigenvectors. In all cases, 3 levels are sufficient to reduce the required number of subspace iterations to 1. Then, using more levels is not efficient as more time is spent on the intermediate levels. This means that the growth rate between the levels of the hierarchy is quite large. For example, for the computations of 750 eigenpairs, on the mesh with 820,000 vertices, the coarsest level has 1500 degrees of freedom. The intermediate level has about 35,000 degrees of freedom, and the finest level has 820,000 degrees of freedom. We compare the performance of HSIM to that of 3 Lanczos solvers we discussed earlier: the implicitly resulted Lanczos schemes implemented in MATLAB and Spectra, and the band-by-band solver implemented in the manifold harmonic solver. We list the timings for different number of Laplace eigenpairs on the Rocker arm mesh with 270,000 vertices. The numbers of eigenpairs ranges from 50 to 2500. In all cases, HSIM was the fastest solver. For more comparisons, including a preconditioned conjugate gradient solver and a multi-level correction scheme, we refer to the paper. Finally, we want to mention that HSIM can also be used for the other eigenvalue problems on surfaces, and the paper includes experiments concerning the computation of Laplace problems with boundaries. and the eigenfunctions of the Hamiltonian operator. More details are discussed in the paper. And to conclude, we introduce the hierarchical subspace iteration method, a multi-grid solver for eigenproblems on surface meshes, and we evaluate HSIM on the computations of the Laplace Beltrami Eigenproblems. Our experiments show an improved performance compared to alternative solvers, such as the commonly used Lanczos-based solvers. Direction of future work includes a revised construction of the vertex hierarchy. The construction of the vertex hierarchy using vertex point sampling yields an isotropic distribution of samples. While this is appropriate for an isotropic operator like Laplacian, one could consider sampling strategies that are operator dependent. This could improve the performance of HSIM for certain types of operators, such as the strongly anisotropic operators. Another direction could be to extend the method such that not only the lowest, but arbitrary eigenpairs can be efficiently computed. Moreover, the method could be improved by further exploring the possibilities of parallelizations of the method and by integrating out-of-core techniques for the computations of large eigenbases. And this concludes my presentations. If you have further questions, you are welcome to reach us by email or to talk to us during the discussion session. Thank you very much for listening.